You know those massive suspension bridges, the ones that stretch for miles and look as solid as a mountain? Well, they've got a secret. They are constantly moving, always vibrating in the wind. For more than 100 years, engineers have just tried to fight this wobble. But a radical new idea is changing everything. It says we don't need to fight the wobble because we might be able to erase it completely. To really get how revolutionary this is, you first have to understand the old rulebook that has governed bridge engineering for decades. This quote right here, it says it all. Vibrations are just seen as, well, an unavoidable part of nature. The thinking has always been, it's physics, you just have to manage it, not something you could ever actually solve.
But what if that core assumption is just wrong? What if the wobble isn't inevitable? Asking that one simple question is the key to unlocking a totally new way of thinking about how we build these incredible structures.
So why do these giants wobble in the first place? Well, it all comes down to some pretty simple physics. Wind slams into the massive surface of the bridge, and the whole structure kind of acts like a giant sail. It has no choice but to swing, pivot, and oscillate. And this isn't just a small annoyance. These vibrations cause metal fatigue, they force traffic restrictions, and in the worst-case scenario, they can lead to absolute disaster. Okay, so let's look at how we've been trying to fight this wobble up until now. For decades, the answer was basically brute force, trying to overpower the wind with sheer mass and tension. But these old ways have some really critical flaws. This chart breaks down the two classic brute force solutions. First, you've got rope bracing, which is basically like adding a bunch of guide wires. The problem is, the way they're anchored, they just end up swinging with the bridge instead of against it, so not much help there. The other approach was to add these gigantic steel trusses to add weight and stiffness, but that creates something called self-loading. The bridge has to support so much extra weight that it's under constant stress, just from its own stabilization system. And if you think those methods really worked, get this: 22 meters. That's the potential sway of Japan's Akaishi Kaikyo Bridge, one of the most advanced in the world during a hurricane. That's over 70 feet. Clearly, a much better solution was needed. And this brings us to the new approach, the cross-force solution. Now, this isn't about just dampening the vibration. It's a complete paradigm shift. It's about preventing the vibration from ever even starting. You know, for 100 years, every solution, ropes, trusses, you name it, has focused on the bridge deck and the cables above it. Everybody was looking up. Turns out they were looking in the wrong place. The solution wasn't external. It was all about connecting the bridge deck to its own most stable points, the very base of its own pylons. The answer was right there, waiting below the roadway this whole time. To get the core concept, just picture a wobbly baby bouncer. It's designed to be unstable, right? But what happens if you take that bouncy seat and connect it to its own base with strings in a cross shape, an X? The wobbling just stops. Instantly, it becomes totally rigid. And that is the fundamental principle at work here. So, how does this actually apply to a massive bridge? Let's break down how this counterforce system works. It uses what's called a double effect that doesn't just reduce vibration, it cancels it out entirely. The key term to know here is dynamic counterforce. See, traditional solutions are passive, kind of like a shock absorber in your car. They just try to lessen a vibration that's already happening. This is different. This is an active force. It engages instantly to stop the first movement and the return movement, basically erasing the whole oscillation before it can even get going. So let's walk through it. Say the wind pushes the bridge to the right. Immediately, the diagonal cables on the left side, which are anchored down at the pylon base, pull taut and just stop that motion cold. Then, as the bridge tries to naturally swing back to the left, the other set of cables on the right side tighten up and stop that return trip. The whole back and forth is completely erased. No oscillation, no resonance. It's brilliant. Here's another great way to think about it: a wrestler's crossbody hold. It's used for maximum control precisely because it stops an opponent from swinging around and building momentum. In the exact same way, this system puts the entire bridge in a stabilizing crosshold against its own foundations. So this all sounds pretty amazing, right? But what are the real-world pros and cons of this new system? Let's take a look. The advantages are pretty significant. First, there's no self-loading stress, like with those heavy old trusses. The cables are basically lazy until they're needed. They only engage when they have to fight the wind, kind of like a seatbelt in a car. This also makes the whole thing simpler and cheaper to maintain. And because it's so light and so effective, it could allow for much wider bridges, stable enough to carry something like high-speed rail. Of course, there is one pretty big drawback: Running all those steel cables down to the base of the pylons can seriously obstruct the shipping channel underneath. Now, the designers are looking at ways to get around this, but for the basic design, it's a real constraint. So we started with a problem that engineers thought was just an unavoidable law of nature. And the solution wasn't some complex new material, but a simple geometric shape. So you have to ask the question, could this simple cross shape, an idea inspired by a baby bouncer and a wrestler's grip, be the key that unlocks a future of bridges that are longer, wider, and more stable than we ever imagined possible?